Okay, this video is about endothermic and exothermic reactions. So if I scroll down past the demonstration reactions that we're not doing right now, clearly, because it's a video, let's look at the definitions here, or the descriptions. A process that gives off heat to the surroundings is called exothermic. So why does that name make sense? Well, exo means exits, and thermic has to do with heat energy or thermal energy. So heat energy exits an exothermic reaction. So the reaction, if it exits the reaction, it also we can say that it releases energy to the surroundings. So in exothermic processes, or mostly we're thinking about reactions, we have heat energy is released. Okay, the other term is endothermic. A process that absorbs heat from the surroundings is called endothermic. So let's break down this term. Endo, think of endo as like into, and thermic is heat energy. So heat energy goes into this process. So in this one, the process itself, the reaction itself, is absorbing energy. So endothermic, heat energy is absorbed. Okay, now it's really important to understand something called the law of conservation of energy, and then we'll use that when we talk about these two diagrams. So in the law of conservation of energy, the total amount of energy is conserved. So energy can't be created or destroyed. It can be transformed between different kinds of energy, and it can be transferred from one place to another. So if we look at these two diagrams, we want to think about which one represents endothermic and which one represents exothermic. Well, on the left, I can see that the arrows are pointed outwards. And so right away, that makes me think of exiting. Whereas on the right, I can see them all pointing into the system. So we're using this term system, but for our purposes, our system is really always going to be a reaction, a chemical reaction. And the main chemical reaction that we're looking at in this unit is a combustion reaction. Okay, so in this one, I can see that the black lines, the black arrows, represent heat energy exiting the system. And where is it going? Well, it's going to the surroundings. So everything that isn't the reaction itself and is around it. So if you're doing a reaction in a container, then the reaction is happening inside of your beaker, for example. And if the reaction is happening inside the beaker, then the heat energy is being released. And so everything outside of that reaction itself would be considered the surroundings. And even if the reaction is happening in some water, then the water could be part of the surroundings as well, and the beaker can be part of the surroundings as well. So the heat energy is exiting, and it's transferring, sorry for my bad squiggly lines, the heat energy is exiting and going to the surroundings. So notice that we have the reaction itself is losing energy, but the surroundings are gaining energy. In this one, the heat energy is going into the reaction. The reaction is absorbing the energy. So this to me looks like an endothermic process. And if I add my term over here, I'd call this one exothermic. So this one is endothermic because we have the black lines, the black arrows representing heat transfer. Heat energy is going into this reaction. So it's absorbing the heat energy. Well, where is that energy coming from? That heat energy must be coming from the surroundings. So the surroundings are now losing their heat energy, and that's going into the reaction itself, into the chemicals. So in this one, we have heat energy absorbed, and we have the surroundings are losing energy. And in this one, they were gaining energy. Well, the way that we can actually measure and recognize that energy is being gained or lost by the surroundings is by measuring temperature. So in an exothermic reaction, because the surroundings are gaining energy, we would expect that the temperature would go up in the surroundings. And so that means that we'd have a positive delta T. So we'd have a positive increase in temperature. Whereas in an endothermic reaction, since since energy is going into the reaction and is getting lost from the surroundings, that means that the temperature is going to decrease in the surroundings. So that means that exothermic reactions tend to feel very warm because they release heat to us. We're part of the surroundings. Whereas endothermic reactions tend to feel cold because we're part of the surroundings and we're losing our heat energy into the reaction itself. Okay, so if we keep summarizing from that, when we have exothermic, we have, again, system versus surroundings. So reaction, and we have surroundings. So in the exothermic, we have the energy transfer goes from the reaction to the surroundings. So we've got the surroundings gaining energy, and we see that as the positive delta T. But how are we going to represent that for the reaction? Well, for the reaction, that energy change must be negative. The total energy has to be conserved. So with this kind of energy, as odd as it's going to seem, we use the symbol H. This symbol stands for this term called enthalpy. And enthalpy is a word used in chemistry to mean like potential energy or stored chemical energy. So sorry if that's a bit odd and confusing, but it basically is just a way to represent the energy in the chemicals themselves. So the fact that it's a negative change means that the chemicals are losing energy, some of their stored chemical energy, and it's going to the surroundings, and the surroundings are gaining the energy. If we flip it around now and we think about an endothermic process, in this one, the surroundings transfer energy into the reaction. And so the reaction is absorbing the energy and therefore gains energy, and the chemicals have more energy after the reaction than they did before. So that the enthalpy change, the delta H, is positive. Whereas the temperature change in the surroundings will be negative. So the signs on these two changes always has to be opposite because the total amount of energy has to stay the same. So if we lose energy, if the chemicals lose energy, then the surroundings will gain it. And if the surroundings lose energy, then it must go into the reaction itself. Okay. Now, we represent these changes also with diagrams called potential energy diagrams or enthalpy diagrams. And if we want to show, let me do this. Let me shrink down what I've done here. Quickly, thank you. Okay. Oh, sorry. Try that again. Okay, so if we want to draw an energy diagram, what we're going to try to do is show, like on a graph with a visual, what's happening to the enthalpy or the potential energy. So if I show potential energy, or I could say enthalpy because they kind of mean the same thing, and then this is the reaction progress over time. So over time, reactants turn into products. Well, in an exothermic reaction, the reactants start out with a certain amount of chemical energy inside of them. And when we're done, the chemicals, which are now turned into products, will have less potential energy inside of them because the change is negative. So in an exothermic reaction, the products have less energy, less potential energy inside of them than the reactants do. And so we end up seeing that the change is negative. So this part of the graph represents the change in potential energy, and we can see that it goes down, so this is a negative change. When we do this for endothermic, again, this is potential energy, this is reaction progress, so as the reaction happens, again, we start with reactants. But in this case, the reaction absorbs energy. And so the reactants, as they change into products, they're actually absorbing energy from the surroundings. And so they end up with more energy than they started with as products. As reactants. And therefore, the change between the reactants' energy and the product's energy is a positive change. So we end up seeing a change like this on the potential energy diagram. So in the first one, where does this energy go when the reactants lose energy to form products? Well, that change then transfers, like we said before. That energy goes to the surroundings and causes the surroundings to warm up. And in the endothermic, where did this energy come from, this delta H positive? Well, that energy came from the surroundings. So energy is getting pulled into the reaction from the surroundings, and that's where the chemicals gain their energy and have that increase in potential energy.